my presentation today is on, in the context of connected autonomous vehicles, looking at a couple of aspects. The first one is in the context of platoons, how do we leverage some of these technologies, and then factor some constraints that show up in the context of these technologies. This particular presentation is also a paper that will be presented at the International Symposium for Traffic and Transportation Theory in Lausanne, Switzerland this July. I wanted to acknowledge my collaborators, Chaoji Wang, Chaoji is here, Siyu Gong, who is a postdoc and now a faculty member elsewhere, Anye Zhou is here as well, so I put them both in italics, they're Georgia Tech students, and Tao Li. So with that, I'll go ahead and get started on the background and motivation for this work. So I'll start with the general outline on what this presentation is about at a very high level, and hopefully that will allow you to get acclimatized to the different aspects that I'll be discussing along the way. So in a traffic network, when you have traffic flow, there can be instability in the traffic flow, which means there's a lot of fluctuations, oscillations, and so on, which affect several different aspects such as mobility, safety, and energy consumption. They have impact on the environment. So all of these are negative effects that are associated when you don't have nice, smooth traffic flow. So that's the first point. The second point is, under connected and autonomous technologies, platoons are being proposed as a mechanism to have traffic flow, whereby a group of vehicles will travel together. And the idea there is that by doing so, they are able to gain efficiencies to address multiple goals as well, because when you do it in a certain way, you can also gain in terms of energy, efficiency, safety, and the like as well. The third point related to this is when you have a platoon and you're looking at strategies which arise from the connected context to enhance the performance of the platoon. One of the challenges that shows up is that the communications between vehicles can have failures. And there are reasons for that. I'll be talking about that. And with this as the background, we propose what's called a cooperative adaptive cruise control strategy, which optimizes the stability of the platoon while factoring communication failures in what I call an active manner. So this is italicized for a reason. I'll be talking about that as I go through the presentation. So let's start with the first point. We talked about instability. So when you have traffic congestion can lead to all kinds of situations which lead to problems in terms of bottlenecks. But also when you have vehicles which are in a stop-and-go type of traffic mode, or in the mode where some vehicles are going slow, others are going fast, this anticipation that would be there typically is not possible. But that's of course when you have human-driven. The same thing can also occur when you have connected autonomous vehicles as well, because in a traffic network, there's always the need to go from one origin to one destination, but each vehicle has its own objectives. So you'll have things like lane changing, you'll have things like where vehicles need to, you'll have spillbacks. So all of these depend on the effect of things like the demand, how much demand is there, then where vehicles want to shift, and all of those. So you can have situations related to traffic oscillations. And the next point, I already mentioned platoon and the motivation for the platoon. And then we have, in a platoon, a leading vehicle, which is shown in green here, the traffic direction. Then you have other vehicles that are following, they're called the following vehicles, so they follow. And what you see here is when you use an adaptive cruise control mechanism, and this is there in existing vehicles as well, in many existing vehicles, whereby each vehicle will follow its preceding vehicle, and to the onboard sensors, there are measurements of position and speed, and these are used by the controller to determine the speed of the vehicle so that it's in pace with its preceding vehicle. So this is a very well-known concept. And then we go to cooperative adaptive cruise control, which is where we are looking at a more system-level control strategy. When we say system, we are now looking at the platoon rather than individual vehicles interacting with the vehicles preceding them. Okay? So in this context, when you have traffic flow, you have the lead vehicle and then you have other vehicles as well. So you can still have the sensors that are determining some information. But in addition, we have vehicle-to-vehicle communication that enables vehicles to send information or receive information from other vehicles. And the key point that I want to emphasize here is while through a ACC, you're able to look at the position and the speed, through this V2V communication, we can also obtain information on the acceleration side. So there is value to this vehicle communicating with this vehicle, okay? Because otherwise you may wonder why you would need that. And through the cooperative adaptive cruise control, the objective is to dampen any traffic oscillations that may be generated. As they go upstream, you want these oscillations to dampen rather than increase in amplitude. Because if that happens, then you have more instability. So this allows us to maintain stable and safe headways between adjacent vehicles. Now, I'm introducing this notion of information flow topology. And what you see here, and here you see the traffic direction now is in this direction, and you have 6 different examples of what we call information flow topologies. And what they show here is the green is still the leading vehicle, and then you have a few other vehicles. And you're seeing how information is flowing from one vehicle to the other or between vehicles. So here is an example of information flowing from the leading vehicle to the next, and from this vehicle to the next one, and so on. Whereas here, you're seeing an example of information flowing from the leading vehicle to a bunch of other vehicles, along with information between adjacent vehicles. So you have different information flow topologies. So this is what we call information flow topology. And so this is an example that we show from this specific paper. And what you note here is the one that we'll be using in this study is called a 2 predecessor following information flow topology. And what that means is any vehicle will receive information from its preceding vehicle and the vehicle that precedes that. So the 2 preceding vehicles are the vehicles you get information. So you get from here and you get from the one before that. Similarly, you have information from this vehicle, and then you have information, for this vehicle you have information from this vehicle and information from this. So that's what is meant by 2 predecessor following information flow topology. I mentioned that part of the challenge when we have vehicle-to-vehicle communication, when we're trying to cooperatively come with better strategies, is that there is susceptibility to communication failures. Okay? And this is something that we have studied in the past. So in a previous study, we have noted that this vehicle-to-vehicle communication, the success rate decreases as the number of, what we mean by equipped vehicles, is vehicles that are equipped with V2V capability, increases. So as the number of equipped vehicles increase in a range, what happens is the failures can occur for multiple reasons. One of the reasons is due to what is called information flow congestion. And that happens because every vehicle is trying to communicate with every other vehicle in terms of sending information, and it also receives information. But as there's a lot of information that shows up as the density of vehicles increase, especially if you're looking at a situation that we'll be looking at in this study, where all vehicles are assumed to be connected and autonomous. So then we have all vehicles that have the potential for V2V communication. So as the density of the vehicles increases, you see that the amount of information that's being propagated across vehicles is so large that the vehicle has a limited ability to handle information, and that can lead to congestion. So what is the meaning of that? So that means that some information that it receives, it will just discard. And so that information may not be propagated. Okay, so that's information flow congestion. The other is called communication interference. And what happens is, if you look at the protocols that are there in the communication, so there are what are called send channels through which vehicles send information. And if two vehicles are competing to send information through the same channel, there will be what is called information collision. And that may preclude information from both of them from being sent. And that is again a failure. Because the idea here is when we are trying to have cooperative control, we are trying to have information sent across vehicles in the platoon. And if that doesn't happen, then we have a failure in communication. And that has an effect on the performance of the platoon as well. And I'll be talking about that going forward. So because of the communication failure, in a real traffic network, depending on the ambient traffic conditions, you'll have different scenarios of the information flow topology. This is an example of what we call a two predecessor following IFT that I explained before without any communication failure. So this is an idealized scenario where every vehicle can communicate with its two predecessor ones in a way that it receives the information, and then the control strategy is determined and it's adopted. From there, here we see examples of four scenarios in which not all information goes across because there is failure of communication. So for example, here we don't receive that CAV2 is not able to communicate with CAV4 or even CAV3 for that matter, if you start with the full ability to communicate across all vehicles. And this is the case where none of the vehicles receive information from their predecessors. And at this point, what happens is you default to adaptive cruise control because each vehicle can see by itself through its sensors is the information coming from its predecessor in terms of position and speed. Okay. Then, from the IFT dynamics, so whatever state we have, each vehicle in the platoon has four possible status indicator values. And the reason for that is the strategy that we adopted, which is the two predecessor following strategy. Okay? So all you have is information from the two predecessors. So there are four possibilities here of the states in terms of what is received. So this vehicle can receive information from its two predecessors. This vehicle can receive information from its two predecessor vehicles. And then you have the case where it doesn't receive information from one of them. You have the case where it doesn't receive information from the other one, or there's no information that's received. Okay, so these are the four possibilities, and this is what we will use later on as well in terms of determining the control. So next, we look at cooperative adaptive cruise control. The standard approach has been to use what is called a fixed IFT, which is, it makes an assumption that there is the information flow topology which vehicles can communicate with each other, and that's the basis for determining the control without acknowledging the dynamics and which arise from the failure. So in this strategy, if the control is based on the assumption that the information flow topology is fixed and all the communications are possible, then the control strategy will lead to an erroneous control actions because in reality not all information is received, so whatever strategy is proposed is not sufficiently good. Or in the limit what you have, it will degenerate to the adaptive cruise control because there's no information that actually is received by any of the vehicles. From there are other studies that have said, okay, in reality, we have dynamics in the information flow topology. Okay? And so we can, at any instant of time, check what is that topology and use that to come up with the control strategy. So that's called the cooperative adaptive cruise control with dynamic information flow topology. And so what happens here is, if you still stick to the two predecessor following control strategy, the following mechanism here, we have 4 sets of controllers that are possible: CACC1, CACC2, CACC3, and the case where none can talk to each other, which will then default to ACC. And what happens is, depending on the instant of time, what situation we have in terms of the IFT determines which controller is then used to count with the strategy. Now, this is better than the FIFT, the fixed one, because it acknowledges the dynamics. On the other hand, depending on the ambient traffic conditions, what that means is, what is the density of flow and so on in that area, the failure probabilities associated with the communication are different. And we actually saw an example of that. We saw the graph related to that. And what we see there is that there are 2 aspects that can affect these communication failure probabilities. The first is the traffic density. So in this case, the ability to communicate, due to interference and congestion that happens. The second thing is what is called the send functionality. What that means is, each vehicle under a V2V communication capability can send information to other vehicles. And depending on how many of these vehicles can send information, that will affect communication failure probabilities. If all of them are activated, it can increase substantially. And so the send functionality is a characteristic that we can zero on. So what that means is, traffic density is traffic density. And in terms of controlling that in a real network, that would be rather difficult, at the level at which you can employ these control strategies. So the question that we had was the following. If we are able to, in real time, activate and deactivate the send functionalities of certain vehicles based on the topologies that would best allow us to maintain the reliability of communication, can we do that? So to address that, we just illustrate a trade-off here. On one end, if there is no communication failure, when we have the fully activated send functionality, so all of them are activated, then the performance of the platoon is the best. Why? Because all the information that's around is shared among the vehicles, which is the ideal situation which we started out with. The other end is, if none of those send functionalities are activated, then we have what's called the most robust one, which is because no communication failure is possible. Okay? On the other hand, what that means is that we are just defaulting to the adaptive cruise control situation here. So the idea that we focused on is, can we optimize the information flow topology to achieve trade-off between the robustness and the performance, so that we can enhance CACC performance in the real world. So what that means is, we have a platoon, we want to come up with, under ambient conditions, traffic conditions, what would be the best IFT to have for the platoon, and then use that to determine which vehicles will have their send functionalities activated, which will have them deactivated, so as to have reduced communication failure probabilities. Okay, so that's the send side. Now, one may ask, what about the receiving side? Because one is send, the other is receiving information. So the receiving failure, related failure, occurs if the distance between some senders is large. Then there are a couple of effects here that we have mentioned, which can lead to failures in terms of receiving information. But for the context that we have in terms of vehicles in a platoon, and ideally what happens, so going forward, one of the expectations is these platoons will have limited size. They're not going to be 200 vehicles, because it doesn't make sense in a real network when vehicles are trying to have lane changes and go to destinations. Simply doesn't occur. So there's a limitation on that. So the spacing between vehicles is small enough that we can assume that a message can be received as long as it is successfully sent. Successfully sent means there's no interference and the congestion doesn't lead to the message or information being lost. And so we adjust the IFT by deactivating these send functionalities of some vehicles in the platoon based on the ambient traffic conditions. So if we go here now, we have a case where some of this got, I'm sorry, some of this got slightly muddled up. But what we have is the case where we have the CAV platoon with two predecessor following IFDs. This diagram got slightly muddled up. I'm sorry, I'm just trying to see how I can, I'm not sure I can fix it here. Apologize for that. So what happens here is you assume these things here. So every vehicle can communicate to its two predecessors. So there's information for this vehicle coming from this vehicle as well as this. So something there got affected. But please look at it in that way. So when we say two predecessors following without communication failures, it's the diagram that I've drawn previously. I apologize for this. And what happens if vehicles 1, 3, and 4 have their send functionalities deactivated, then information can flow only from vehicle 0 and vehicle 2. In reality, because it's two predecessors, this will go from here to here as well, and this will go from here to here as well. But remember, the next two are shown correctly, where only we have vehicle 0, so that's the degeneration scenario, where vehicle 2 fails to send its message, only vehicle 0 can send the message. So this is what you have. The other case where only vehicle 2 can send its message, you have this case, okay? And that's what we show out here. So here, when you say 10100, it's saying that this is the scenario in which vehicle 0 and vehicle 2 are sending the information. Here, vehicle 0 is sending the information. Here, only vehicle 2. And here, none of the vehicles are. Okay, so these are the 4 cases that we illustrate in terms of the 5 vehicles. Okay. So, with that, we come up with the following. If you recollect, I mentioned that when we talk about communication failures, there are probabilities associated with that. So the probability that a platoon with a particular IFD, so I showed an example of an information flow topology, operates under